All right, let's talk about something slightly different, but still the same. The operating principle. For the yoke. Or the probe. Kind of mix the two up in there. So, what do I want? I want that one. Current slide. All right, so we talked about that. We got that. Did all that. All right, so there we go. There is my yoke. So is my yoke going to be direct or indirect magnetization? Indirect, because the power is going to come in. Oh, it makes this so Steve can see it. I'm going to say it the rest of my life. Power goes around here, creating what kind of magnet? Electromagnet is correct. So the electromagnet is right here. Is there any electricity flowing this way? No, none at all. So we just have an electromagnet. So we have indirect magnetization goes through here, and that's just that simple. That's what you get.
It's almost like the magneto.
It is a little bit like the pole shoes and stuff. And hey, maybe we can use the magneto to make. Could we use the magneto to make to do this test?
Yeah.
No. I don't think so. I don't know. Okay, so yoke. A yoke is a handheld device that uses an electromagnet. Typically, they use 110 volt house current, although some newer models use 220. More power. All right, may have two settings. May have two settings. Some of them actually you can control the power a little, I've seen. Ours does not. Ours is just fixed. What are my two settings? AC is one of them. Best for what kind of indications? Surface. Surface defects or surface indication. Why? It's actually a little bit different. Well, we can skin effect, but there's a different reason in it this time. Yep. Okay. Causes. I'll just tell you, causes the media to be more mobile and sort of dance around. So if the media is jumping around and moving, it's going to jump and move over towards the indication or the discontinuity. So if I'm doing that, am I doing continuous or residual? It's got to be continuous, because if I do residual, then there is no AC. It's just magnetism. So it causes the media to, quote, dance, which increases mobility and makes the media more sensitive. I don't mean more sensitive like, I'm not picking on anyone.
That's all you thinking, Kevin.
I was going to say PK.
I'm sure you
I've seen him crying in the car a couple nights. He gave me a C. Where's wrong with that guy? All right, another setting, half wave DC, used for. I was gonna say used for subsurface, but I don't know. It's there. Sure, you can use it more for subsurface. I've proven that you can use the AC just fine for subsurface. Of course, that's what we can go with the book says. So used for subsurface. but you're going to lose sensitivity, and that to me that's kind of a, well, are you sure about that? Because if you're going to lose sensitivity, then you're going to have a harder time finding defects. You have a harder time finding defects, and have a harder time finding subsurface. But anyway, that is kind of the way it goes. So let's see. The field induced, the field which is induced in the yoke, travels down the legs and induces a magnetic field in the part. So the field induced in the yoke travels down the fully articulating legs. I'm not going to write that. Down the legs and induces a magnetic field in the part. Now I will tell you that I never used one of these in the field. Well, it'd be ridiculous to use one on an engine. I think you'd have to be a little bit crazy. I suppose maybe you could get away with using one on a crankshaft flange, but I don't know why you would do it, and I wouldn't know if I didn't find an indication, I don't know if I would continue to, trust it. Just like, well, didn't find one, now let's take it apart and do it the right way.
We're good.
I suppose there could be potential to use it maybe on a motor mount or something, because they're made out of steel. I don't know. Let's see. Oh, we said this. It is indirect. Indirect magnetization. So no current is flowing through the part. So if no current is flowing through the part, it's indirect. What does that sound like if we think about the bench?
Coil shot.
Okay, coil shot. So it's circular or longitudinal here? Okay. Longitudinal. Magnetism is parallel to the legs. Does that hold up in our picture? Magnetism is in fact parallel to the legs. Discontinuities will show up transverse to the legs. So longitudinal, I'll just 1, 2, 3. So discontinuity will show 90 degrees to legs. What kind of media do you suppose I would use?
Social media, sure.
Yep. I want to show it doesn't count if I don't post it on Instagram that I even did it. So I can't.
Bird, you gotta take a selfie.
You did it. Did you put it on social media? No, but I wrote it in the logbooks. Well, that's how we used to do things. Can use wet or dry media. So if I'm going to use wet, what do I got to do? I got to take it over to the Magnaflux booth, put it inside the Magnaflux booth. I got to turn on the pump. I got to stick it in there and do that. Why don't I just use the bench? Is that the way it works? Okay, portable things. So what kind of portable wet media would I possibly have? Spray on, aerosol can. I've got a whole bunch of them in there. All right, can use wet or dry media. Because B-E-C-A-U-S-E, there's an E there, because of its low strength. We really should spend some time, if you guys don't have anything for tomorrow, we can get it out, use the Tesla meter on it, see what kind of Gauss we're getting out of it, compare that to something else. We could even possibly use some wet media on it, not wet and dry at the same time. But because of its low strength, what kind, should I use wet or dry on it?
Dry.
Why dry then?
I just remember the demonstration.
I did use dry, but is that the best thing?
No.
Yes.
It's easier clean.
What's that?
It's easier to clean. You said something about it, or because of the air.
Oh, there we go. Man, this guy's on it.
50-50.
Oh, 50-50. Nah, but he's got it. Dry powder.
You picked it up with the yoke. with powder.
So, I could have picked up the wet stuff too. Could have picked up the whole can with it.
That's what I wanted you to do.
Okay, because of its low strength, dry powder is typically used. Now you just have to tell me, why dry powder? Why is dry powder going to be better than wet?
Gas, air is a gas, and wet is liquid.
What's that? Hang on.
So air is a gas,
There's a gas.
and the molecules moving faster.
Okay.
And the bath is a liquid,
Okay.
so it's more or less like air is more than a layer of this layer, so it's easy to like a dry powder can easily go inside.
Is that what you were trying to say?
I remember the air portion. I can't. Not the.
Mobility, right?
Yes.
Is it lighter?
Can you run faster
Yeah.
Yes.
on the side of the pool or in the pool?
Either.
Nobody should know because you're not supposed to run near a pool. Can you run faster in water or out of water?
In water. Out of water.
Okay.
Out of water.
Because
Less resistance.
less resistance.
Less resistance.
Same thing. So there's less resistance. So the particles will move easier in air. So dry.
Yeah, unless you're a water creature.
Unless you're a fish.
Let me see. How do I have too much written down here? So dry dry. I know. Dry has more mobility.
Very carefully.
More ability than wet. I'll just leave it at that. I'll explain why. Usually done with continuous. Why is it done with continuous? Okay, done with continuous because continuous is more sensitive, and we want AC to make the particles dance and move about. If I don't have it on, how well are they going to dance and move it out? They are not. So usually done with continuous, and for a couple of reasons. Continuous is always done on parts that have
High retentivity. Low retentivity.
low retentivity. All right. All right, now so I gave you a demonstration. So you put the yolk on there, energize it. You have a little blower, and you blow the particles on there, and you can actually get another blower and blow the little particles around that are already on there without having to add a bunch more. We'll just go to this one, EFGH, demagnetize. Well, how are you going to demagnetize with the yolk?
Depends on which way you magnetize it.
Well, we could use reversing, diminishing, DC. How fun would that be?
Not very.
So the yolk has to be, yolk is, let me see. All right, that's reverse. Yolk position. And move away with each shot or simultaneously. So you'd have to pick it up just a little tiny bit and rotate it, hit the button, and then what's going to happen when you do that? Part's going to jump up and hit it, and you got to start all over again. So you got to hold it down if it's a plate or something. But if it's something mounted, and well, if you're using this on a bridge, the bridge isn't going to move. So you just back and forth each time and kind of walk away from the part you're doing. Or
Do you constantly hold the button, or do you like pull, press, release,
press release. I prefer AC, so just diminishing AC. Turn it on and just slowly pull it away, and you're done. All right, we also have, in addition to that, we have, what do I have on my slides here? We got that. There we go. This is actually the pictures I took when I was in the school. So they just had a little handheld one there. And there's all the powder. I don't know, you can't really see the indication too well. Oh, these are those weld plates I was talking about. So if you looked, yeah, can you see it? Let me see. Right here. There's a crack right there. Okay, we also have permanent magnets. What's that? Permanent magnets with a cable between them. And I tell you my theory, why is there a cable that holds them that way? Well, two reasons probably. One, so you don't lose them. If you lose them together as a pair. But two, I believe this cable will not allow this end to touch this end, because I believe if this end were to touch that end, I don't know if you get them apart again. So there we go. So it's the same principle. You just apply this on there. Is this going to be continuous or a residual method? Can I use residual? Not if they're on there, because it's just on. You can't turn them off. Caution, powerful magnet. Oh, implanted medical something as pacemakers don't use.
Prop 65, that's what it's saying.
Was it last year or the year before? I had a really cool student. We were doing a bunch of stuff. We had the small machine, but we were demagnetizing stuff, and he was reaching in and through. But he had a implanted insulin box.
Did it fry it?
I don't know. I'm like, dude, is that going to be a problem? I don't know. Never saw him again. I don't know. All right. So anyway, cracks there.
Good point.
All right. So we also have the permanent magnets. They say it works just like a DC yoke, because they don't make AC magnets that I'm aware of. Prince, they make AC magnets yet? What are you looking at me that for? All right. Then we have prods. Maybe prods would be a nice thing to have to get people to actually get their projects done. All right. So our handheld electrodes. Current is passed through the part. So if it's passed through the part, you have a risk of arcing. If you have a risk of arcing and you are in a pipe, because remember, a lot of this stuff is designed to be used for oil and gas, so you have been assigned to inspect the inside of a large pipe. So you climb in there with this, and you've got your aerosol can, and you get a nice arc.
You're going to blow yourself up.
Yeah. Nice eyebrows. What would happen to them? Risk of arcing. So what kind of magnetism does it create? Circular or longitudinal? Direct is circular. Let's see, discontinuity. We'll show parallel or perpendicular to the path of electricity.
Parallel.
All right, you guys are good. Parallel. Flow of current. Therefore, if I have a prod here and a prod there, would my indication show this way or up and down? be crosswise.
Yeah.
Parallel with the current, because this is the plus and this is the minus, or back and forth, either which way. Yeah,
Why would you want to use these?
I don't know. I've never used them. I don't want to.
So-
It seems like a bad idea.
Yeah.
I did not enjoy using them at all.
Yeah, this seems like it really.
This seems like a bad idea, right?
Well, it definitely seems like the pipe industry. Or
Oh, absolutely. I wouldn't use this on an aircraft. Let's see if there's any breaks in the aluminum skin, right? Okay. So these are the prods. They're supposed to be held about 6 to 8 inches apart.
68
68 inches. What, and again, this is, you can tell this are my photographs. What we're trying to do here is, because the teacher didn't know, is you can only detect going this way. Well, this is molded, and so we couldn't check any cracks going this way on this plate. So I said, you guys follow what I'm saying?
Yeah.
Okay, so I said, well, what if we laid another plate on top? Could we then check for cracks going this way in this plate? No. No, we could not. So, no, I did not very much enjoy the prods at all, and they were not fun. I think I was going to get myself shocked there, so. All right. Oops. Yeah, we're wearing rubber gloves. It's possible to get shocked. Okay, where am I here? So, let's see, discontinuity, parallel, let's see. D, you can use wet or dry media. And limited to about 800 amps. I don't think they make it much bigger than that. The thing that sucks is you really had to push hard on them to make sure you had good continuity. What's that?
There's a risk of arcing.
Yeah, the higher you get, of course. Yeah. Let me see. Well, a lot of extraneous notes. A lot of this we've already talked about, so maybe we can you can take some notes without me having to write them down. So that's really all the processes. So from here on out, it really just becomes kind of fine-tuning things we've already talked about. And one of the things is, I've called it process control, making sure that your machines work, everything is set up. That's all part of the NDT process. And like we've already learned kind of from day one, that's part of the stuff that a level 1 should be able to do. Turn on and calibrate the machine, make sure everything's going. So one of the things that you always have to do, especially with a wet bath that's open, is what? According to the picture,
Concentration.
got to check my bath concentration every day. So that's something I did every single day. I think if you ran shifts, you have to check it every shift. There's actually quite a bit of carry-off with this. Carry-off is where the particles are on the part, and then you take the part. If you guys actually start to notice our bench is starting to get piled up with the iron filings. So one of the things I would do periodically is before I would just add more of I'm calling filings, but the media to the bath, is I'd actually clean my Magnaflux machine. Just take a rag or something and just start wiping it. I actually use the fluid, and just wipe it all down and get that buildup that you have back in the machine. You'd be surprised how much concentration goes way up. So you kind of have to be careful with that. But you got to check that every day. And you want to check it for at least an hour, let it settle out in a vibration-free environment. One of the things I've cautioned you about is I've left it like this for the weekend and came back in on Monday, and I could not get that out. I mean, this stuff just settles and packs in there like you wouldn't believe. And so I have to get a welding rod in there and kind of poke it out. And this little tube right here is, I don't know, this is about $100 for this piece of glass. Stand's probably $500, who knows? What's this?
It's state of the art, that's why.
It is. What is this called? No?
Centerfold too.
A centrifuge, which implies that it spins around in circles. Please don't hold it and spin. It's very, very pricey. All right, so that's one of the things we have to do. The Ketos ring. All right, so the Ketos ring, we want to check that. We put it on a central conductor. And let me see, do I have my numbers? No, I don't. So we want to get with a DC machine, we're going to check it at, I don't know if I wrote it down here. Let me see. Yeah, I did. All right, so over here, my pen. So we're going to check it. I check mine every day, and I'm going to check it at 1400 amps, and I should get 3 indications. Which indications do you suppose I'm going to get? 1, 2, 3. Then. Okay, 14, then 2500, and I should get 5 indications, and check it again at 3400, and I should get 6 indications. 1, 2, 3, 4, 5, 6.
That's a big jump to only get one from 25 to 34. Only get one more indication.
Yeah, you only go from here to here. But, okay, experience. You guys are in there working with me on our machine. How many indications am I going to get about at 3400?
Like 6 or 7.
Like 6, yeah. 1, 2, 3, 4, 5. Well, I got to get at least 6. 1, 2, 3, 4, 5. No, 5 or 6. I'm getting them all the way up into here, right?
Yeah, but it kind of goes into a gray area there.
Okay, so there it is. He's right. It's you can see them, but it kind of goes in this like gray area where it's like, well, there's an indication, but only because you know where to look and you're kind of interpreting what you expect to see. So it's almost a confirmation bias situation where like, I should see something, so therefore I am. And you can make yourself kind of see that. But I don't know. These things are what, $500-$600 at least.
You drop it, you have to send it in and get it calibrated.
And you can see it comes with the calibration certificate. It really does. And because you never know when these holes might shift. And so it's a joke.
That's why I said if you drop it, you have to send
Yeah.
it in for calibration.
Now, when you test with the ketos ring, does it have to be at a certain temperature?
Not that I'm aware of. I don't know what temperature would make any difference because it's Magnaflux, magnetic particle inspection.
Curious.
You run enough amps through it to get warm. All right, so that's what it looks like. But now, what's nice is, last time I taught this class, this is all you got to see. We didn't have one. And we didn't have a machine that would even get one indication if we did. So now you guys have all got to experience it. And you're like, I've seen it. Been there, done that. All right, pi gauge. Why is there a 9-volt battery? Because I took these photographs when I was at school. I'm like, well, nobody's going to know how big that is. So I saw a 9-volt battery sitting there, so I threw that down. It's the same size as a 9-volt because it's battery operated.
How big is a 9-volt battery?
Our batteries included.
Yeah. It's a very small piece of pie. It's very disappointing. So we have a pi gauge. What's the pi gauge used for?
Checking your indications.
Yeah. So I guess we could call the Ketos ring this too, but it has a different function. A Ketos ring is used independently. These are not used independently. They're actually going to be used with the part that you're looking at or trying to inspect. So we call these like known defect indicators, or I have a fancier word I was going to use, artificial discontinuities. So this right here, has anybody not got to see this in operation? Oh, really?
Yeah.
Oh, we got to get this back out then. So what this does, oops, laser pointer. Yeah, laser pointer is good. So I'm going to take like a crankshaft and lay my crankshaft in the Magnaflux machine, and I will lay this on top of it. Now, one thing, I'll be very honest with you. This side, you can see it has a piece of steel and then a piece of non-ferrous material, like copper or something like that in here. So you actually have a discontinuity between each one. And if I flip it over, it's just copper on the other side. It's all copper. So it's very smooth. There's nothing to it. So I'm a little unsure if you are supposed to use it on this side or the other. I use both sides because I think it's kind of cool. If you use the other side, then it's like a subsurface. This side to me is surface. So, but you lay this on the part and hang on to it and magnetize your part, or treat this as part of whatever you're inspecting. So I got a crankshaft in there. I'm just going to sit it right there on the crankshaft. I got to hang on to it, put my wet media all over it, hit the button, and this thing should light up in the right direction of what I was doing. So if I've got it laying and the crankshaft is laying this way, like the tail stalks here and the head stalks here, I should get indications across this pi gauge. Which way would my indications be going? This-
Along the axis.
Okay, so I should get one here, and I will. And I'll get one here, and I should get one there. How about here? Not going to get anything. So if I get these showing up, I'm good. I'm getting some magnetism through the machine that would at least pick up that kind of discontinuity. Like I said, I can flip it over where it's totally smooth, and that more simulates to me subsurface. And I should see the same indications pop out at me where it was, and it's a piece of copper, so it's not going to hold very well. This has very little retentivity, so need wet continuous. So that's the pi gauge. These are QQIs, qualitative quality indicator, QQIs. They're actually not very big at all. What is that, centimeters? No, it can't be centimeters, it would be like millimeters. These things are small. I should have had a 9-volt battery in the picture. But what you do is they're just little stickers. You can't use them they're not really reusable because you lose the stickiness. But you take it off, you stick it on the part. And it's like having a pi gauge. But you don't have to worry about dropping the pi gauge down in the bath. So it's just going to stick to the part. And of course, you got to worry about there being a crack underneath this. But anyway, stick it on the part, and you should be able to get an indication on this indicating that your machine's working. So it's like taking a piece of metal and sticking a discontinuity right to the surface of the part. So that's what these are. So there's different types. There's the circular type you can get. There's these little pluses you can get. I kind of like the pluses, although I don't really use these. In theory, I like the plus better because I should see, if I got it in one way, I should get it one way, and then the coil, I should get it the other. So, QQIs. Sheet metal shims. Yeah, that's all I got. So, oh, hey, there's a guy
Is that
using
your
magnet.
partner?
That's not me.
No, I know that. I said, who is that guy?
Who's that guy? He's the guy on the internet. The internet.
He doesn't have a cool machine.
So, you know what though? But I like this tailstock better with that and that. That's how mine was. It was easier to
Is
use.
that his light up above?
Yes, and that's one of the reasons I think why I left this in here. I like that light. That's pretty
Yeah,
sweet.
Then you can't take it off and.
I know. I prefer the one that can go right in front of my eyes and kind of aim it. So, but again, last year, hey, this is how I had to explain what a bench looked like. People didn't know. They're like, bench, okay, I see. At least you got a picture, And I said, oh, someday maybe we'll have something nice like this. And guess what? Someday's here. That's a teeny tiny one. Oh, that's not even a Magnaflux machine. What is that? That's a DMAG machine. All right, so,
Look at that crack.
all right, got some cracks.
I love a good crack. Magnaflux joke.
I know, got it. Got to get the lights. Want me to can you reach it?
It's gonna look like Christian's notebook.
Okay, so I kind of like this picture here for a couple reasons. One, is this a crack?
No.
How do you know?
That's leakage.
What's that?
Well,
Well, okay, it could be
the one
leakage.
on the right looks like an indication. The one on the left looks like flux leakage.
All right.
Look the same to me.
The way I would, so when I see that, I can't just dismiss it. I'm going to watch its behavior. One, I will, if there's a puddle here, I'll try and blow the puddle away. Two, I'm going to see what it does on the other side. If it starts making a corner, going down a little bit, I got a problem. So here's a keyway. So I got this right here in this keyway. So is that a crack or not? You'd say probably not. Then I look right here, and if that's going this way, oh yeah, that's really cracked. So how that crack comes around the keyway.
Even in the lower part, in the hollow section, it looks like curvy too. Like it's not straight, like you can see in the radius bins, that's like more of a straight line, but if you look down you can see it like turning,
Okay.
like
Yeah.
more
Yeah.
spidering, like it's
Okay.
cracking.
Yeah, I think so. All right. That is a busted crankshaft.
Yeah.
It looks like it.
It's a crack.
I don't think I took this picture. I don't know.
Someone just spinning it on the wood.
We've got some crankshafts that look just like that.
Whoa.
So where's the crack at?
Okay, so we're gonna. I took this picture. It's a picture of a photo that was at the school,
You took a picture of it?
and so You guys have a sick sense of humor here.
That was Hawaii.
This is real. Passengers on Aloha inter-island flight in Hawaii had the shock of their lives when 24,000 feet up, the roof of their Boeing 737 was torn off. The air hostess died and 56 were injured, but the pilot managed to land the topless aircraft on a runway. 25 miles away, investigators found evidence of cracks and corrosion in the 19-year-old plane. 7 years earlier, an aircraft had broken up in the same way. This was a big deal when this happened. I remember it quite clearly. It sucks that somebody had died, but what they found out is that due to corrosion that was not found, that this just departed. You got a cabin depart light going on there. And so this set up a whole need for eddy current inspections that started to go. So what we're going to do, a little bit of time we have tomorrow, is we're going to talk a little bit, not much, about eddy current, ultrasound, and stuff like that. But this sort of kicks it off. So if you're going to be in aviation, people will talk about the Aloha incident, and this is it. So, all right, so we'll leave it at that.
So they're not supposed to be converted? Why? Only when it's meant to be.